Hello, my name is Krista Galloway.
And I'm Nick Baer. This is the design, development, and implementation of a 5-band equalizer. For this project, we decided to design a 5-band signal equalizer. The purpose of this project is to take an incoming AC signal and modify its frequency response to a desired new state. This circuit was chosen due to an interest in audio applications and its use to demonstrate various filters and how they can be used for audio purposes. For this equalizer, we decided to go with a 5-band equalizer system, comprising of 5 different filters and amplifiers to be added by a signal adder on the way out. We chose to do this in 2 separate banks, passive and active. We chose to split these instead of doing them in single circuits so we could better modify our low-pass, band passes, and high-pass filters without modifying our amplifier gain. For adjusting these values, we were able to use potentiometers to adjust the various resistor values of both our passive circuits and our amplifier gains. The main objective of this project was to design and implement an electronic circuit application. The circuit was designed theoretically, simulated in LT-SPICE, then laid out in dip trace and ordered for PCB printing. This equalizer was designed so the signal would be only affected by one band at a time, each band having a feedback potentiometer that can range from 0 to 10 kiloohms. The cutoff frequency can also be controlled using different sized potentiometers. The bandpass bands have 2 potentiometers, so that the upper and lower cutoff frequencies can both be adjusted. The PCB was designed using the software DipTrace and printed online using the printing service PCBWay.com. Here is the circuit diagram for our circuit as seen in LT-SPICE, the software we use to simulate it. And here is our PCB layout as built by DipTrace. On the left and on the right is a photo of our final circuit after being printed and soldered with its final components.
So, we were able to test out our 5-band equalizer, and we did find that each of the 5 bands do work. Looking at the table 1, we see some values that we got for the low pass as well as the first band pass filter. We have the frequency values as well as the feedback resistor values. We tried to get a low value for the feedback resistor as well as a higher value for 2 of the bands so that we could compare how the band operated as well as to see how efficient each were. Figure 4 and 5, we have figure 4 on the left, figure 5 on the right. Both have the input voltage as blue and the output voltage as red. And we wanted to show that both the amplitude and the phase for both values were very similar. The percent error we found was much larger when the feedback resistor was smaller. We believe that this could be due to current noise. We also believe this could be due to some mismatching of resistor values based on real-life values versus simulated values, and we can control simulated values much more accurately than we can for real-life values for those resistors. In conclusion, we did find that our equalizer was operational, with some bands working better than others. As Nick mentioned before, the software we used includes LT-SPICE and DipTrace, and we were able to use PCBWay.com to get our PCB board ordered and printed. Like I mentioned before, our biggest issue that we found was the fact that our percent error was much larger when our feedback resistor was small. We recommend using a larger input resistor as well as a larger feedback resistor in the future so that the gain itself does not change, but then there's going to be a decrease in current noise. And if we do have mismatched resistor values, the percentage difference will not be as much. We would just like to give a big thanks to our professors who were able to help us out with the design and development of this project. We really appreciate it. Thank you. Now, we'd like to go on to the experimental side and show you guys a little bit about how each band works and how the waveforms will change based on the potentiometer values. Hello again. We're going to do a quick demonstration to show the use of our 5-band equalizer system. We're going to show how the amplitude can change based on the value of the feedback resistor. We're going to show how all 4 of the other bands are in cutoff when one band is in operation. And then we're going to show how you can change the bandwidth of the band that is in operation by showing its cutoff frequency based on the potentiometer. Nick, take it away.
Here's a demonstration of the low-pass filter operating at 1.7 kilohertz. Here's adjusting the feedback resistor, showing how the amplifier gain operates. Now demonstrating how the other amplifiers do very little to no effect on this band. Finally, demonstrating the cutoff adjustment of our low-pass filter. As we increase this resistance, you can see the band enters cutoff. And now, a demonstration of our first bandpass filter as you change the feedback resistance. Notice how the other amplifiers change very little about this band. Also, as I adjusted the amplitude of the feedback resistor, our noise level dropped significantly. And now, a demonstration of our second bandpass filter as you change the feedback resistor. Please note that during construction of our PCB, it became apparent that one of our components was malfunctioning. Unfortunately, we did not have a spare component for this piece, and so we were forced to improvise. Because of this, the overall effectiveness of this filter has been diminished, and as we change the feedback resistor, the gain is unfortunately not as high as we would have liked.
I'm now going to show you how our third bandpass band works, operating at 13 kilohertz. As I increase the feedback resistor, you can see the amplitude of our wave does increase. As was true of all bands, if I change the feedback resistors of any of the other bands, there is minimal to no change to our output waveform, as expected. I'm now going to demonstrate our fifth and final band, our high-pass filter, operating at 18 kilohertz. As with the other bands, I'm increasing the feedback resistor, and you can see how our output signal is increasing substantially as our feedback resistor is increased. Our cutoff doesn't happen quite as quick as our low-pass band, but you can also see when we start to put it into cutoff, our waveform does decrease in amplitude. Until it is completely in cutoff. That's our 5-band equalizer system. Due to some component failures, we were unable to get all 5 bands working exactly how we hoped for in terms of amplitude spread, but all 5 bands did work correctly by the end. In the future, if we were to make changes, we would make our input resistor as well as our feedback resistors slightly larger so that we have the same level of gain, but then we wouldn't have as much noise in our current noise. Thank you so much for sticking with us and have a good day.
Here's a demonstration of our first bandpass filter as you adjust the feedback resistor. Nope, I'm going to do it again.
Okay, you ready? Okay.
Here's a demonstration of our first bandpass resistor. With the magic of video editing, I cannot sound like a power drill.
Yeah, right.